All right, we are going to be talking about power functions and polynomials. So a power function, this is kind of an obscure term. You don't have to worry too much about it, but it's something that has this form. Okay, some constant k and an x raised to a power. So k and p just need to be real numbers. Okay, and k is the coefficient of this x to the p. So is this a power function? It is. In this case, k would be 1 and p would be 0. Here, the identity function, that is also a power function, right? In this case, k is 1 and p is 1. Quadratic, yep, k is 1, p is 2. Here, cubic, yep, p is 3. How about if we have something like this, like the reciprocal function? Is this a power function? It is. The exponent for x would be -1, which is a real number. So this is a power function. Same with this one, right? The exponent would be -2. What about square root of x? Yep, the exponent would be 1/2, and that's a real number, or 1/3 for the cube root function. So that's the idea of power functions. So let's talk about the end behavior of power functions. All right, and honestly, thinking about these, the ones we're going to care about are these up here, okay? Ones with integer exponents. That's the ones that are going to be interesting to us because we're going to be talking about polynomials in a minute. So what if the exponent is even, like 2, 4, or 6? Okay, so we can see those three graphs and they're pretty similar, right? We're pretty familiar with the green parabola, right, for a quadratic. X to the 4th, x to the 6th, not so familiar, but they look a lot the same. And if we were going to describe them, maybe we'd say they're just getting like flatter, right? But what we want to look at right now is the end behavior, okay? We don't care really what happens here for now. We just wonder what happens when x gets really, really big in the positive or negative direction, okay? So we can see they all go up, right? And the way we would describe that mathematically is as x goes to positive infinity, right? So as we go along the x-axis, f of x goes to infinity. And this is the mathematical notation we would use. And we could write it as x goes to -infinity, right? So as we go along the x-axis to the negative side, f of x goes to infinity, right? So we're using this arrow notation, and we say this as x approaches infinity, f of x approaches infinity. All right, so this notation is something that's going to be important to practice. What about if we have odd exponents? So x cubed, x to the 5th, x to the 7th. Again, we can see there's some patterns here in what the graph looks like. And, it gets a little bit flatter as the exponent gets bigger. But the end behavior is the same, right? It goes up to the right and down to the left. So we would say as x approaches -infinity, f of x approaches -infinity. And as x approaches infinity, f of x approaches positive infinity. All right, so again, this notation is something that we'll need to practice. All right, so here's a little summarizing graph. These are the two we looked at. If we have even powers and the exponent or the constant in front is positive, it's going to go up on both sides. And if it's odd, it goes down on the left and up on the right. Well, if the coefficient in front, the constant in front, this k value is negative, less than 0, it's going to reflect the graph, right? So this is going to go down in both directions, and this will go up to the left and down to the right. Or mathematically, as x approaches -infinity, f of x approaches infinity. That should be a negative right there. That's not right. These are flipped. And as x approaches infinity, f of x approaches -infinity, right? It should approach -infinity on both sides, so that's a mistake. And as x approaches -infinity, f of x approaches positive infinity, so this should be a positive right there. So this is also incorrect. And as x approaches infinity, f of x approaches -infinity. So sorry about the mistake on this slide. All right, so let's describe this end behavior. Not sure exactly what x to the 8th looks like. We can imagine it's probably going to be kind of like x squared, right? Since it's an even exponent and that has a positive coefficient. So I think it's going to go up on both sides. Sure enough, there's the graph. And we'd say as x approaches in positive or negative infinity, f of x approaches infinity. Okay. How about this? What if f of x equals negative x to the ninth? Okay, well, x to the ninth is going to be like x cubed, except it's flipped, right? So it's going to go up to the left and down to the right, up to the left and down to the right. And it's pretty flat there because that exponent's pretty big. So as x approaches negative infinity, f of x approaches infinity. And as x approaches infinity, f of x approaches negative infinity. That's how we would mathematically express that. Okay, so now let's talk about polynomials. So n is a non-negative integer, and a polynomial function is a function that can be written in this form. Okay, it's got all these terms added together, and each term has some coefficient, and then x raised to that power, and those powers just go down, right? So if this was a fourth degree polynomial, then we'd have a fourth term, a cubed term, a squared term, of x to the 1 power and x to the 0 power. So this is the general form. When it's in descending order of powers, the a coefficients can be any real numbers. This one can't be 0, right? Because we need, if it was, then that term would just disappear. And each of these we call a term of the polynomial function. And all of these exponents must be integers, okay? So which of these are polynomials? Is this a polynomial? Yes. If we multiply it out, right now it looks kind of messy, but if we multiplied this out, we would have something of it in this general form where the exponents would all be integers. And how about this one? Again, it's not in general form right now, but if we multiplied this out, we would get like negative x cubed minus 4x, and that would be a polynomial. So yes, these are polynomial functions, even though they're not in general form. How about this one? 5 times the square root of x plus 2. No, because, why? This exponent is 1/2, and that's not an integer. Okay, so we're not dealing with any square roots or cube roots. And it also has to be positive. Sorry, I didn't emphasize that. So nothing like 1 over x. Okay, just what you expect and have been using as polynomials, that's what polynomials are. No weird terms like cube root of x or 1 over x squared or anything. Okay, so here's some terminology. This is the leading term. This whole thing is the leading term. This number is the leading coefficient, and this is the degree. Okay, so the biggest n, right, the biggest exponent of x, that's what tells us. It's not the ordering of these terms, because we can always reorder terms, right? It is which degree, which exponent is the biggest. So that's the degree, that's the leading coefficient, and this whole thing is the leading term. All right, so here, let's see, this has the biggest exponent. So this whole term, this is our leading term. Our leading coefficient's -4, and this is a third degree polynomial, or a polynomial of degree 3. All right, let's look at this one. Here's our biggest exponent. So our leading term is 5t to the 5th. Power of the degree is 5, and the leading coefficient is 5. How about this one? This term here, biggest exponent, degree 3. The leading term is negative p cubed, and the leading coefficient is -1. All right, so let's think about the end behavior. Oh, it says power functions, I meant of polynomials. Okay, so the end behavior of polynomial functions, the good thing is all we do is look at the leading term. Okay, we ignore everything else because when x gets really big, for end behavior, we're going to infinity or negative infinity, right? X is getting really big. The only term, the term that's going to dominate everything is this biggest one. Okay, so whatever the biggest exponent term, the leading term, that's the only one we care about for end behavior. So you can see some wonky stuff might happen in the middle, right? But, oops. Okay, this is not a correct graph. Ignore this graph here. That is not the graph of minus this function. Okay, so ignore that. But let's look at these three. The leading term here is 5x to the 4th. It's an even polynomial with a positive coefficient. So it's going to be like x squared. It's going to go up on both sides. How about this one? We've got an even term, a negative leading coefficient, so it's going to be reflected and go down on both sides. Sure enough. Here we've got an odd coefficient with a positive leading term, so it's going to be like x cubed. It's going to go down on the left and up on the right. And ignore this, that is not correct. Okay, so let's look at this graph. Describe the end behavior and determine a possible degree of the polynomial function. Okay, well, as x goes to infinity, f of x goes to positive infinity. And as x goes to negative infinity, f of x goes to negative infinity. That's a fancy way of saying up on the right, down on the left. And a possible degree, well, this is like x cubed, right? So it's going to be odd, right? It's going to be odd with a positive coefficient. Okay, what if they give us a function, a polynomial, and they ask us to express it in general form and determine the leading term, degree, and end behavior? Okay, so they've given it to us nicely factored, and they're asking us to multiply it out to put it in general form. So we multiply these terms, and then distribute this term out front, and we get something of this form, right? And you might want to practice that. If that looks like it might be confusing, you could pause and just make sure you get that same answer. All right, so now this is in general form. So what can we tell? It's an even coefficient with a negative, it's an even power. It's an even degree polynomial with a negative coefficient. So this is going to be like x squared, except flipped, right? So as x goes to negative infinity or positive infinity, both sides are going to go down. And then let's talk about leading term is this one. The degree is 4, and the end behavior we talked about. Okay, so that's end behavior right at the end, but we also sometimes care about what happens in close, right in the middle of the function. So we call that local behavior. So here are the things we care about: intercepts, like x-intercepts, y-intercepts, and these things called turning points. Okay, so a turning point is a point at which the graph changes from increasing to decreasing or decreasing to increasing. And the y-intercept is where it crosses the y-axis, and the input value is 0. And the x-intercepts are where the output value is 0. We've talked about input x-intercepts and y-intercepts before. Okay, so turning points might be the new idea a little bit. All right, so given this polynomial, written in factored form for our convenience, determine the x and y intercepts. All right, so for the y-intercept, right, that's when x is 0. So we just plug 0 in to this function. We'll get -2 times 1 times -4, which gives us +8. How about finding the x-intercepts? Well, they happen when in any of these terms equals 0, right? So that's going to happen at x equals 2, x equals -1, or x equals 4. And sure enough, we look at the graph, and that's where the x-intercepts are. Okay, so in order to find the x-intercepts, we have to have it in factored form. All right, so here they give us a function that is not in factored form and ask us to find the intercepts. So to find the y-intercept, we can just plug it right in. We can probably do it in our head, right? If we put in 0 for x, we're going to get out -45, right? Easy. How about to find the y-intercepts? We're going to have to factor this. Pause the video and see if you can do it. All right, this is a little bit tricky. We have to kind of factor this as if these were squares. Does that make sense? So from here to here is pretty tricky, and we haven't practiced that a ton. So if that seems kind of tough, that's okay. I wouldn't worry too much about it. But if you got it, good job. That was very clever. We can write this as x squared minus 9, x squared plus 5. And now we can write this as a difference of squares. We can't factor this anymore. So what do we get? We have y-intercepts or x-intercepts at 3 and -3. And we can't factor this in any way to get any more solutions. So our x-intercepts would be at 3 and -3. And sure enough, this is what the graph looks like. You do not have to know how to graph this. Okay, you could put this in Desmos or in your calculator, but at this point, I would not expect you to be able to graph this. We're going to put this together in a few lessons, and you'll start to be able to graph them, but don't worry if you didn't construct this graph. So here's our x-intercepts, here's the y-intercept, and that didn't ask us for it, but these are turning points. And in order to find the turning points, you're going to have to go to calculus next year. Okay, we don't find them in this class, but in calculus you do. All right, so intercepts and turning points. We can't find the turning points, but we do know sublimits. A polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. So think about the graphs that you know. Like a quadratic is degree 2. It can have at most 2 x-intercepts and 1 turning point, right, the vertex. Or x cubed, think about what the x cubed graph looks like. It can have at most 3 x-intercepts and 2 turning points. Okay, so without graphing this, we've got a 10th degree polynomial. Find the maximum number of x-intercepts and turning points. Okay, so it can have at most 10 x-intercepts and 9 turning points, right? That's all there is to it. You look at this number, 10 x-intercepts, 1 less, 9 turning points. All right, what if we have a graph? Let's try to conclude some things about this based on its intercepts and turning points. So first of all, what degree do you think this is? Is this even or odd? Well, it goes up on both sides, so it's going to be even, right? So it's an even degree polynomial. How many turning points? It has 3 turning points, right? Here's one, here's one, here's one. So if it has 3 turning points, it has to be at least degree 4, right? It only has 2 x-intercepts, but you could imagine if this was shifted up, I mean, at most it could have, if it was shifted, it could have up to 4 x-intercepts. So I think this might be a 4th degree polynomial. So the end behavior tells us it's even. And the graph has 2 x-intercepts, so it's degree 2 or greater, and 3 turning points, suggesting degree 4 or greater. So the degree is probably at least 4. Maybe it's 6, maybe it's 8. We don't know. What about this? If we have this function, determine local behavior. So we could find y-intercepts, just plug 0 in, right? We know what the x-intercepts are, 0, -3, and 4, right? Whatever makes each of these terms 0. And turning points we're not sure about. So we find the x-intercept, we find the y-intercept and the x-intercepts, and it's degree 3, right, if we were going to multiply this out, so it has at most 2 turning points. Whoops. And that's the end of this section. So those are the things in this section that we want to talk about for polynomials and power functions. End behavior, like if it goes up or down, and local behavior, what the intercepts are and how many turning points.